Addressing concerns from an inspector regarding exposed cords above a suspended cloud typically involves several key strategies. Firstly, clearly explain the intended purpose of the cloud. Emphasize that it functions primarily as a reflective for indirect lighting and serves as an aesthetic architectural element rather than a structural ceiling. This distinction is crucial. Secondly, demonstrate that the exposed cord does not create a safety hazard. Explain how the cord will be securely attached to the T-bar grid and will not pose any tripping risks or impede access to the area above the cloud. Providing detailed plans or diagrams illustrating the cord's placement and securing methods can be very helpful. Thirdly, research and refer to relevant industry standards and building code interpretations that support the argument that the cloud is an architectural feature and not a structural ceiling. Many codes distinguish between ceilings and architectural elements, and presenting these distinctions can strengthen the case. It is also helpful to request a site visit, inviting the inspector to personally assess the installation and better understand the context and functionality of the cloud within the overall lighting design. Besides directly addressing the inspector's concerns, several practical solutions can be considered to achieve compliance. One option is to use a flexible conduit to enclose the exposed cord. Selecting a conduit color that closely matches the cloud's color can make it less visually obtrusive and more aesthetically acceptable. Another possibility is to install the cord above the cloud entirely, completely removing it from sight. If this is feasible, ensure that the cord is properly supported and secured to prevent any potential hazards. If neither of these solutions is ideal, it is worth attempting to negotiate an alternative solution with the inspector. This might involve allowing a small, manageable portion of the cord to remain exposed for necessary access while installing a discrete shielding device to minimize visibility and potential hazards. Review precedents and case studies of similar installations where inspectors have permitted exposed cords above suspended clouds, provided it's clearly demonstrated that the cloud is not a structural ceiling. Some building codes may have specific provisions or interpretations regarding architectural features that are not considered ceilings, which could support the argument. Additional tips include being thoroughly prepared with supporting documentation and evidence to present to the inspector, such as product specifications, installation diagrams, and code references. Consult a licensed electrician or contractor who can provide expert technical advice and assist in ensuring compliance with all relevant regulations. Maintain a professional and respectful demeanor in all communications with the inspector, fostering a collaborative approach to finding a mutually agreeable solution. If necessary, consider escalating the issue to the building code official or higher authority if a satisfactory resolution cannot be reached through initial discussions. When dealing with electrical installations, several fundamental principles must be followed to ensure safety and code compliance. Understanding conductor ampacity is crucial, as it determines the maximum current a conductor can carry continuously without exceeding its temperature rating. National Electrical Code (NEC) Table 310.16 provides ampacity values for various conductor types and sizes based on insulation type and ambient temperature. For example, a 12 American wire gauge (AUG) copper conductor with type THHN insulation, rated for 90 degrees Celsius, typically has an ampacity of 30 amps, but this may need to be derated based on ambient temperature and the number of current-carrying conductors in a raceway. Voltage drop is another critical factor, especially in long circuit runs. Excessive voltage drop can cause lights to dim, motors to overheat, and other equipment to malfunction. The NEC recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. To calculate voltage drop, the following formula can be used: voltage drop equals 2 times K times I times D, divided by circular mils, where K is a constant for the conductor material, approximately 12.9 ohms circular mils per foot for copper. I is the current in amps, D is the one-way distance in feet, and circular mils is the cross-sectional area of the conductor. Grounding and bonding are essential for safety. Grounding provides a low impedance path for fault current to return to the source, allowing overcurrent protection devices to trip and clear the fault. Bonding ensures that all metallic parts of the electrical system are at the same potential, minimizing the risk of electric shock. The NEC requires that all metal enclosures, raceways, and equipment be properly grounded and bonded. Overcurrent protection devices, such as circuit breakers and fuses, are designed to protect conductors and equipment from overloads and short circuits. The size of the overcurrent protection device must be matched to the ampacity of the conductor it protects. NEC Section 240.4 outlines the requirements for overcurrent protection. For example, a 14 American wire gauge or copper conductor typically requires a 15 amp circuit breaker. Wiring methods must comply with the NEC requirements. Common wiring methods include rigid metal conduit, intermediate metal conduit, electrical metallic tubing, flexible metal conduit, and non-metallic sheet cable. Each wiring method has specific applications and installation requirements. For example, rigid metal conduit provides excellent physical protection and is suitable for wet locations, while non-metallic sheet cable is commonly used in residential wiring. Electrical boxes are used to enclose wiring connections and protect them from the environment. The NEC specifies the minimum size and type of electrical boxes based on the number and size of conductors entering the box. Box fill calculations ensure that the box is not overcrowded, which could damage conductors or create a fire hazard. Proper labeling and identification of electrical circuits are essential for safety and maintenance. The NEC requires that all circuits be clearly labeled with their purpose. Panel schedules should be accurate and up to date. In commercial installations, emergency lighting and backup power systems are critical for life safety. Emergency lighting must provide adequate illumination for safe egress in the event of a power outage. Backup power systems, such as generators or uninterruptible power supplies (UPS), provide power to critical loads during power outages. These systems must be regularly tested and maintained to ensure their reliability. Considering specific requirements for indirect lighting installations is very important. Indirect lighting relies on reflecting light off surfaces to provide illumination, which can create a softer, more diffuse light compared to direct lighting. When installing indirect lighting, it's important to consider the reflectance of the surfaces the light will be bouncing off. Lighter colored surfaces will reflect more light than darker colored surfaces, resulting in higher illuminance levels. The placement of the light fixtures is also critical to achieve the desired lighting effect. The fixture should be positioned to maximize the amount of light reflected off the ceiling or walls and to minimize glare. The type of light source used in indirect lighting can also impact the overall lighting quality. LED, light-emitting diode, lamps are a popular choice due to their energy efficiency, long lifespan, and ability to produce a wide range of colors. However, it is important to select LED lamps with a high color rendering index (CRI) to ensure that colors are accurately rendered. In office environments, lighting control systems can be used to optimize energy efficiency and improve occupant comfort. These systems can automatically adjust the light levels based on occupancy, daylight availability, and time of day. Daylight harvesting systems use sensors to detect the amount of natural light entering the space and dim the electric light accordingly, reducing energy consumption. Occupancy sensors turn off the lights in unoccupied areas, further reducing energy waste. Addressing the inspector's concerns regarding the suspended cloud requires a multifaceted approach. Demonstrating the cloud's non-structural function, ensuring quad safety, referencing applicable codes, and potentially modifying the installation with conduit or alternative routing are all viable strategies. Maintaining open communication and a collaborative attitude with the inspector is crucial for achieving a compliant and satisfactory outcome. Remember to always consult with qualified electricians and adhere to all applicable codes and standards to ensure a safe and effective lighting installation. Finally, to provide additional clarity on the NEC, consider some specific examples. NEC Article 310 addresses conductors for general wiring. As mentioned before, NEC Table 310.16 provides ampacity ratings for conductors based on insulation type and temperature rating. For example, a 12 American wire gauge (AUG) THHN copper conductor in a raceway with no more than 3 current carrying conductors has an ampacity of 30 amps when the ambient temperature is 30 degrees Celsius or 86 degrees Fahrenheit. However, if the ambient temperature is higher, or if there are more than 3 current-carrying conductors in the raceway, the ampacity must be derated according to the tables in NEC Article 310. NEC Article 250 covers grounding and bonding. Section 250.118 lists the acceptable grounding conductors, which include copper, aluminum, and copper-clad aluminum. Section 250.122 specifies the minimum size of equipment grounding conductors based on the rating of the overcurrent protection device. For example, a 20 amp circuit requires a 12 American wire gauge (AUG) copper equipment grounding conductor. NEC Article 400 covers flexible cores and cables. Section 400.8 lists the prohibited uses of flexible cords, which include using them as a substitute for the fixed wiring of a structure, running them through holes in walls or ceilings, or attaching them to building surfaces. NEC Article 430 addresses motors, motor circuits, and controllers. Section 430.22 specifies the minimum ampacity of motor circuit conductors, which must be at least 125% of the motor's full load current rating. Section 430.52 specifies the maximum rating of motor branch circuit, short circuit, and ground fault protective devices, which depends on the type of motor and the type of protective device. For example, an inverse time circuit breaker protecting a standard motor must not exceed 250% of the motor's full load current rating. NEC Article 500 addresses hazardous locations, which are areas where flammable gases, vapors, dusts, or fibers may be present. This article classifies hazardous locations into different classes, divisions, and groups based on the type and likelihood of the hazard. Each classification requires specific types of equipment and wiring methods to prevent explosions or fires. NEC Article 517 covers healthcare facilities. This article includes requirements for essential electrical systems, which provide backup power to critical loads during power outages. It also includes requirements for patient care areas, such as the use of isolated power systems to reduce the risk of electric shock. NEC Article 547 addresses agricultural buildings. This article includes requirements for wiring methods, grounding, and bonding in agricultural buildings, which are often exposed to corrosive environments and livestock. NEC Article 600 covers electric signs and outline lighting. This article includes requirements for the installation, wiring, and grounding of electric signs and outline lighting. NEC Article 680 addresses swimming pools, fountains, and similar installations. This article includes requirements for bonding, grounding, and ground fault circuit interrupter (GFCI) protection to prevent electric shock hazards in and around swimming pools and fountains. Always consult the latest edition of the NEC and local codes for specific requirements. Understanding and applying these principles and examples will aid in ensuring safe and compliant electrical installations, especially when dealing with unique architectural features like suspended clouds and the associated inspection processes. Remember that working with electricity can be dangerous, and it's always best to consult a qualified electrician or electrical engineer for guidance. Also, always adhere to the manufacturer's instructions for any electrical equipment being installed. The goal is to maintain the highest safety standards and ensure that all installations meet or exceed the requirements of the applicable codes and standards. Keep in mind that local amendments to the NEC can vary, so it's vital to be aware of any specific requirements in your jurisdiction. Consistent communication and a willingness to address concerns proactively will contribute to a successful and compliant installation.